Beautiful. Okay. So let's chit chat about that whole concept of significant figures. So they kind of seem like random rules, you know, what's the whole point? So here's the bigger idea, and if you keep this in mind, and we'll go out and we'll do some data collection here in just a second. Here's just your overriding theme. You can't make a calculated answer look more precise than the data that you have to do the calculations. Okay, that's it. If you just keep that in mind. You got sketchy data, you can only have sketchy answers. If you've got really good data, then you can have really good calculated values. Because that's, at the end of the day, that's what we're doing. We are using data that we collect to plug into equations to see if that matches what we think is happening in the universe. Okay, that's it. That's what we're doing. So if I have a formula that I predict how long it takes for this thing to follow a certain distance, it's great. I have a formula. But if I can't measure the time, if I can't measure the distance with a high degree of precision, then I can't make that happen. Like one of the greatest challenges that scientists face was actually measuring the speed of light, because speed of light is an incredibly fast number, and we'll talk about that today. So the speed of light is 3.00 times 10 to the 8th meters per second, okay? And to give you some perspective on that, so there's 3.00 times 10 to the 8th meters per second. So the speed of sound, which is also a pretty fast number, so the speed of sound is about 343 meters per second, okay? So, and it isn't like this, and thankfully the speed of sound is a pretty big number, because otherwise, if it wasn't, there would be like a time delay. Like you would see me say the words, and if the speed of sound is really slow, then it would take a while for that sound to get to you, and it'd be like really weird, like you see my mouth move, and then like a second later, oh, then you hear the words, and everybody would just kind of be flipped out. So that isn't an issue. Speed of sound is still pretty fast. And if you ever get a velocity faster than the speed of sound, ask yourself, is that really possible to go faster than the speed of sound? So if you're doing a calculation of a beagle as it's chasing a squirrel, and you get the velocity of the beagle to be like 600 meters per second, odds are you probably did something wrong, because I doubt Snoopy the beagle is going to be traveling faster than the speed of sound. Okay, it's probably not going to happen. So there are certain values along the way. It's like, hey, is this reasonable? If you ever get a velocity remotely close to the speed of light, you probably did something wrong, okay? Like orbiting satellites, the fastest velocities we will calculate are about 10 to the 3rd meters per second. So if you ever calculate a velocity and you get like 10 to the 8th meters per second, like, or even 10 to the 6th, like, oh, I've done something horribly wrong. So to give you an idea of how fast that is, if you look at the Earth, and we're kind of on a decent-sized rock, okay? Nothing compared to Jupiter or Saturn, but, you know, it's the decent-sized rock. So if you were to stand at the equator, say about Nairobi, Kenya, and you could shoot a beam of light, you turn on a flashlight and that beam of light goes out. And instead of going straight, you could make that beam of light follow the exact circumference of the Earth. It would take you about 1/10 of a second for that beam of light to come and make it all the way around the Earth. Okay, 1/10 of a second is about how long it takes to snap your fingers. So that's just to give you some perspective on just how fast the speed of light is. Literally, you turn on the flashlight, boop, that long, it has made it all the way around the Earth. Not like from here to the back of the room, okay? That's all the way around the Earth. So that's a pretty big number. So that became one of the challenges. Like, how do you measure something that fast? It isn't like, you know, we're going to go out and I'm going to have, I don't know, I'm going to have somebody go out and run. We're going to go out and run 10 minutes or run 10 meters. And we can sit there and we can watch this person run and we can time it. Okay, it's cool, right? We can't do that with a beam of light. We can't say, okay, hey, somebody turn on the flashlight, and then we'll watch the beam of light, and then we'll stop the stopwatch when it hits a certain point. It's a huge technological challenge just to get that value. So when you look at when we express this 3.00 times 10 to the 8th meters per second, that has 3 significant digits, because whenever you put something in scientific notation, hey, 3.00, 3 significant digits. So we know the speed of light, and it's a pretty solid number, 3.00. It isn't like it's 3.00527321, whatever, okay? We got a pretty good idea what it is. There's some uncertainty to it. Y'all have, in chemistry, tell me somebody recognizes that number, 6.02 times 10 to the 23rd. Carson?
You want me to say what it is?
Yeah, what is it?
Avogadro's number?
Yeah, Avogadro's number. Here's the irony of it. We call it Avogadro's number, but Avogadro never actually came up with a number. Okay? He came up with a concept, but he never actually came up with a number. So, again, you have 6.02 times 10 to the 23rd, 3 significant digits. So when we do calculations involving Avogadro's number, the speed of light, whatever that is, that means we have some uncertainty in it. We only know that value to a certain degree. So because of that, when we use these numbers in calculations, we can't make our answers look better than the data that we have. So when you get to, like let's say for example, on number 10b, okay, we're going to look at a sum of some masses. We have 18, 84, 0.94, 1.0, and 9.778. And conveniently, these are all in kilograms. Okay, that's cool. I couldn't add them if they weren't all in kilograms, right? So here's the story when you add or subtract numbers, okay? When you add or subtract numbers, the easiest way to figure this out is that you look at the least precise measurement. And the easiest way to do that is stack them up and find the least precise value. Well, that's that 1884. So since this is only known to the nearest whole kilogram, when I add these numbers together, I can only have that value to the nearest whole number. Now, if that had been a 0.0 on the end of it, hey, that's a completely different degree of precision. If there had been a 0 on the end of it, then I could round this answer to the nearest 10. But it isn't. So in other words, we took all these measurements, okay? Hector, he's measuring something big, 1884. Okay, that's about the mass of a car. Okay, that's a lot of kilograms. So Hector's just going, man, I'm measuring the mass of a car. I only know that to the nearest whole number, okay? Now, you got 0.94. Hey, that's a really small, okay, 0.94 kilograms. Okay, we had a different scale that was measuring that. We got 1.0. That's a different scale because that's measuring to the 10th. Then we got this one, which is cool because go tens, hundreds, thousands. Okay, cool. That's a very precise measurement. But because my least precise measurement is to the nearest whole number, that's where I have to round that to, is to the nearest whole number. When you're adding and subtracting, this has nothing to do with the number of significant digits. Don't look at this and go, oh, 1.0. That has 2 significant digits. I can only have 2 significant digits in my answer. It's not the point. No, bad. Don't stop. Whoa, bad. Okay? When you're adding, subtracting, it's a place value. So come out here, stack this. So your answer to number 10 should be to like the nearest whole number. There should be no decimal places on the end of your answers to 10, on your answer to 10b. Okay, so your answer to 10b, there should be no decimal points on the end because the nearest value is to the nearest whole number. So add all these up. The oracle is going to speak to you. The oracle is going to give you an answer. Take that answer, round it to the nearest whole number. Okay? When you get to questions 12, 13, and 14, okay? So on 12, 13, and 14, all of those are division problems. So when you divide, it's a different set of rules, but it's the same idea. So when you multiply or divide, it's the least number of significant digits. So if you look like on number 12, you have 6.60 times 10 to the negative 8th, okay? That has 3 significant digits. The 3.3, that has 2 significant digits. So what that tells me on number 12, your answer has to have 2 significant digits, okay? Your answer to 13, is going to have 3 significant digits. Your answer to 14 is going to have 3 significant digits. So on those, make sure that you have the correct number of significant digits and the correct units. Now, let me give you all a hint, because we're going to do a lot with scientific notation. When you're punching these numbers into your calculator, if you punch in like the times 10 to that exponent, a lot of times if you don't punch that in exactly right, you're going to get answers that make no sense whatsoever. Okay, like you're going to get the most bizarre answers in the world. It's much better if you use that EE key. That EE key takes the place of the times 10. Okay, you can use the times 10, but it's a lot of work. And if you don't put brackets around everything just right, you get answers that make no sense. So a lot of times when you look at answers, we want to get what's called an order of magnitude. In other words, we just want to get an idea of what the answer is. So if you look at, let's say, for example, on number 13, you have 10 to the 10th divided by something times 10 to the 3rd. Okay? So just on what we call an order of magnitude. Order of magnitude is a fancy word by saying, hey, what's the exponent going to be? Okay, so y'all have done work with exponents in your math classes. So when you take, and you have 10 to the 10th and divide it by 10 to the 3rd, do you add the exponents or do you subtract the exponents? Subtract. So as a ballpark answer, I know my answer to number 13 should be something around 10 to the 7th. Okay, just if I look at my exponents. Okay, so if I don't have something times 10 to the 7th, I've done something wrong. Okay? Now, when you get to number 15, okay, so let's talk about number 15. Because 15 is historically one of the most missed questions on this assignment. So looking at your assignments right now, just out of idle curiosity, how many of you have an answer of 0.025? Does anybody have an answer of 0.025? Or 2.5 times 10 to the negative second? Okay? So? Okay? All right. Your answer is wrong, by the way. Okay? This is what we're going to talk about. And here's the reason why. You're subtracting. True? Okay? So when you subtract, what do you worry about? Number of significant digits or place value? Place value. So when you get to a question like a number 15, write that out old school. Write it out in normal form. Oh, I got 2.67 times 10 to the minus second. I'm going to write that as 0.0267. Okay? I'm going to write that out. Space it out. Then I got 1.5 times 10 to the negative third. Oh, that's 0.0015. Okay? So if you write them out, even though they have different exponents, they actually are, these measurements are actually show the exact same precision. Okay? They have the exact same precision. So when you subtract this out, and you get 2520, that is your answer. Okay? So here's what typically, this is why I talk about number 15. Okay? Typically what you do on number 15, you see that 1.5 and you say, oh, that has 2 significant digits. My answer can only have 2 significant digits. Okay? That would be true if you were multiplying or dividing. But when you're subtracting, what you want to look at is what's the precision of those measurements. These measurements, even though they have a different exponent, have the exact same degree of precision. Okay? So that should be your answer to number 15. Okay? All right. Let's talk about 31, 32, and 33. So I want to work these. I want to make sure everybody knows exactly how I want this done. So this is going to be the most common conversions you do in this class. A conversion of kilometers per hour into meters per second. Without fail, it is the most common conversion you're going to do. So I want to make sure everybody knows exactly how I want this done. So let's start off with 31. You have 108 kilometers. And you want to convert that into meters. So on your equation sheet, your big dog equation sheet, which you will have on the test. So on the test next Tuesday, what's going to happen? So you have, if you want to get into that mindset, I'm going to hand out the test, and I'm going to give you all a laminated version of the big dog equation sheet. Okay, you will always have that available to you on the test. Okay, I'm not going to make you memorize random equations. Boom, here. You just have to know how to use it. So on your equation sheet, there's a conversion that says, oh, the conversion from kilometers, okay? Kilo means 1,000. So 108 kilometers, to give you some perspective, because we're used to thinking in miles. 108 kilometers would be about 50 miles, which is kind of roughly the distance from here to like Cassidy. If you've ever driven the turnpike going up to Kansas City, okay? So that's about the distance from here to Cassidy, to kind of give you some perspective. So we want to convert that into meters. Oh, okay. 1 kilometer, 1,000 meters, boom. The kilometers cancel out, you get meters. So hopefully at some point in your esteemed mathematical and science careers, you all have been taught what's called this factor label method. If you don't know this process, learn this process. It is phenomenal, okay? And it works because of the fact that it eliminates mistakes. So if you've done chemistry, you know, which I'm guessing that you all have done chemistry. You all learned stoichiometry, okay? If you had Mrs. Schertz, or, you know, I'm sure you learned, 1 liter is 1,000 milliliters, okay? You all have learned this factor label method. If you don't feel comfortable with it, come in during Encore, come in before school, go, hey, Burkamp, can you help me out with this? This is one of the most important skills that you have to have. So, I'll multiply this together. Now, I have 108. How many significant digits are there in 108? 3. Okay? It's easy. There's no decimal places. There you go. So there's a couple of different ways that you can write this answer. One option is that you can write 108,000 meters. It's cool. That works. Does 108,000 meters have the same number of significant digits as 108? Yes, because there's not a decimal place. These zeros are freshmen. They're just taking up space, but they're not significant. Okay? That's all they're doing. So that's an option. If you're like, oh man, Burkamp, I like scientific notation. Oh, so do I, right? Consider it for the nerds. So you can also write it as 1.0 times 10 to the 5th meters. Personally, I like this because then I don't have to look at your paper and count the number of zeros. Okay? That's why I like this. Now, if you don't like writing times 10 to the 5th, the other option is you can do 1.08 e to the 5th. Okay? So if you just want to put e to the 5th, it's like, man, Burkamp, I hate writing times 10. Okay, fine, don't write times 10, just put e. All right, cool, whatever, it works. Okay? So there's your answer to number 31. Okay? And the beauty of this is, no matter how you write it like this, they still have the same number of significant digits. You still have 3 significant digits. Okay, now we have 1 hour. Now this is exactly 1 hour. I'm going to show you 2 ways that you can do this. This is a personal preference thing. How you do this, you need to make this decision, figure this out. So one option is you can go 1 hour, and then I'm going to put 1 hour down here. 1 hour is 60 minutes, and then 1 minute is 60 seconds, and you get 3,600 seconds. Okay? So that's an option. Now, this is exactly 1 hour. This isn't like a measured value. So 1 hour is going to be exactly 3,600 seconds. Okay, there's no variation on the thing. This is not a measured value. How long did you go? About an hour. No, that's not what we're saying. We're saying 1 hour is always going to be exactly 3,600 seconds. So you can either do it in 2 steps where you go hours to minutes, minutes to seconds. If you like that, it's like, oh, that speaks to me. Cool, I'm happy for you. The other option is that you just shortcut it and you go 1 hour, put 1 hour down here, and just go straight to 3,600 seconds. Whichever one you want to do makes me no difference. You can either go 60-60 or just go straight to 3,600. Now, a word of caution. If you go 1 hour is 3,600 seconds, and sometimes I see this, if kids screw this up, you will put it as 1 hour is 360 seconds and not 3,600. So if you're going to go straight to the seconds, it's cool, you can do that. Just make sure you're using 3,600, not 360. And I don't know if y'all have flashbacks to geometry and it's a circle and then there's 360 degrees in a circle and maybe that's your flashback, I don't know. But if you're gonna go straight from hours to seconds, make sure you use 3600 and not 360. Okay, so those are your answer to 32. Now on 33, I got 120 kilometers per hour that I'm going to change into some number of meters per second. This is the most common conversion that you are going to do, okay? I promise you, this is the most common conversion you are going to do. You're going to do this, and I promise you, on the test on Tuesday, if you hand your test in on Tuesday and you haven't converted from kilometers per hour into meters per second, you have done something wrong, okay? It is the most common conversion you're going to have. So I'm going to show you exactly how I want this done. So first off, Jaden, I have 120. How many significant digits are in that value?
2.
2. There's not a decimal point. It's like, how fast are you going? About 120, okay? 120 kilometers per hour is about 65 miles per hour to kind of give you some perspective. So if you're driving 120 kilometers per hour, this is like highway speeds, okay? So, and it's an estimate. How fast are you going? About 120. Okay, I'm not saying I'm going 120.0. Okay, it's a ballpark. How fast are you going? It's about 120. And sometimes that's all you need. Hey, how fast you go? 120. So I'm going to show you exactly how you need to do this. So I'm going to set up this deal. I'm going to take the 120 kilometers, and put that over 1 hour. Okay, so stack this like a sandwich. You have 120 kilometers on top, and then I'm going to have 1 hour down below. Okay, and fundamentally that's what that means. Okay, I'm going 120 kilometers in 1 hour. That's what that means. It's a rate function. Okay. Now I always deal with the kilometers first. So I'm going to come down here. I'm going to put 1 kilometer, and then I know there's 1,000 meters in 1 kilometer. Okay. So if I stop right here, if I don't do anything else, Tyler, what units do I have?
You have meters over hours.
Yeah, I have meters per hour. If I don't do anything else, at this point my units are meters per hour. Okay, not what I'm after. I want meters per second. So here's the next step. So I have hours down here, so I'm going to put hours up here, because that way I can cancel out the hours. Okay, so I have hours here, I'm going to put hours up there. So I'm going to put 1 hour up there, okay? And then I'm going to put 3,600 seconds down here. So the beauty of this is everything's going to cancel out. The only thing I have left are meters per second. So if you want to shortcut this process, you can actually like lop off a couple of zeros. So the short version is that you take the number of kilometers, you multiply by 10, and you divide by 36. Okay, that's the short version. Because in this process, the only thing that will ever change is the number that goes up here. 1 kilometer is always going to be 1,000 meters. 1 hour is always going to be 3,600 seconds. So the only thing that you ever change is the number that goes here. Okay, that's it. That is the only number that you're going to change. So basically, you multiply by 10, and then you divide by 36. So to convert from kilometers per hour to meters per second, multiply by 10, divide by 36. Okay, that's the short version. So somebody let me know, what do you get out of that with give me that answer with 2 significant digits.
33 meters per second.
33 meters per second. Now, here's another thing that you will see. And this is a little self-check that you can do. Because you're multiplying by 10, and then you're dividing by 36, when you convert from kilometers per hour into meters per second, your answer mathematically always has to be smaller than what you started with. If you convert from kilometers per hour to meters per second, and you get an answer bigger than the kilometers per hour, you've done something wrong. Okay? So that's a little self-check that you can do along the way. Hey, I'm going to convert kilometers per hour to meters per second. If you get an answer bigger than what you started with, you've done something wrong. Okay? All right, so there's your answers to 31, 32, and 33. Don't miss them. There's your answers, okay? All right. Anybody have any questions at all on any of the remaining ones? Like if there is a shadow of a doubt? Peyton?
On 13, are the units still newtons per second?
Yeah, you can just put newtons per second. That's the easiest thing to do. Just put newtons per second. Bailey?
Okay, so on number 15, I had my brother help me on it, and he said that I had to, like, when I was subtracting it, like, the exponents have to be the same. So he told me to make 2.67.267 times 10 to the negative third, and then just subtract 1.5 from it.
Well, you could do that.
But it's not the same answer as what you
No.
said.
He just did that because if you have the same exponent, then you can do the subtraction easier. He was just looking at it from the pure mathematical side of it, okay? But that has no impact on the rules of significant digits in terms of how you express your answer,
Okay.
okay? So that's why if you go old school and you just write them out of that normal decimal and don't even worry about the exponent, okay? If you just go out and write them, stack them out, that's why I said if you do this,
Yeah.
okay, those have the exact same precision.
Okay.
So that's why you just end up with the same answer. You could write it, you could put that in scientific notation. You could put it back and call it 2.52 times 10 to the minus second if you
Okay.
wanted to. But because of the fact that you're talking about measured values, both of them have the same precision, so therefore you have to have that same place value out there on the end.
Okay.
Okay? Talk to me, Hector.
Number 32,
On 32?
yeah,
Yeah.
it says that it's 1.00 hours.
Yes.
So that means it's 3 digits.
But on that one, I'm telling you, 1 hour is exactly 3,600. That isn't a measured value. The only reason I had you do 32 is so that you realize then when we get to 33, that 1 hour is exactly 3,600 seconds. Okay, that's not a measured value. 1 hour is exactly 3,600 seconds. That isn't, well, all I want you to, I just did that so you knew that 1 hour was 3,600
So it
seconds.
would be the same, it would say like 1.0 kilometers, it would be still
Yeah,
1,000.
yes.
Okay.
Now, if I said, hey, how far did you run? 1.0 kilometers. If it's a measured value, then you have significant digits. But in terms of just the conversion, 1 hour is exactly 3,600 seconds. 1 meter or 1,000 meters is exactly 1 kilometer. So there's no uncertainty in the conversion. The uncertainty comes in the measured value. Okay? Talk to me, Miss Elliott.
Can you go over 17?
I can. Okay. So on 17, you're multiplying, right? So I have 2.5 times 10 to the negative 6 meters per second, okay, which is a really slow velocity. Okay, that's probably about how fast your fingernails grow. Okay, it's a really small velocity. And then I'm going to multiply that by 3.0 times 10 to the third seconds. Now, because I'm multiplying, do I worry about place value or the number of significant digits? Okay, true. Good answer. So 2.5 has how many significant digits? 2. 3.0 has 2 significant digits. So I know my answer can only have 2 significant digits. So that's the first part of the puzzle. Okay, so I know my answer can only have 2 significant digits. In terms of the units, I'm going to multiply meters per second times seconds. So when I multiply meters per second times seconds, what units do I get? Meters. So right away, I know my answer can have 2 significant digits, and my units are going to be meters. So if all goes well, your answer should start with a 7. Okay? And you can either put it in scientific notation, or you can write it out as a decimal. Carson, did you have a question?
Oh, I was gonna ask if we could go over 30, but I think I got it.
Okay. So on 30, let me give you some, because sometimes I see some weird answers on 30. So we're gonna deal with cube roots, especially when we get into planetary motion. So you got the cube root of 26 seconds cubed. So fundamentally what I'm asking is what number can I multiply by itself 3 times and get back to 26? Okay, that's fundamentally what I'm trying to find. Okay? What number can I multiply by itself 3 times to get back to 26? Now, Carson, 26. How many significant digits are there in 26?
2.
2. So that whatever I have here can also only have 2 significant digits. Okay? So if you're not sure, take your calculator, punch in 26, and you can, there's any number of ways you can find the cube root of it. One option is that you go 0.333, and you raise it to that decimal. Or you can go 26 to the 1/3, okay, if you want to do fractions, okay? But here's the story. This answer here, okay, here's what you can do to check your answer. Take your answer to number 30, cube it, and see if you get something around 26. If you do, you probably did it right. If you don't, something's gone wrong. So your answer to 30 should be between like 1 and 5.
Yeah.
Good?
Mhm.
Okay. Anything else at all you might have an inkling, I'm not sure if that's right. Angel, talk to me, man.
11, what's the name by like the least precise measurement?
Okay, so on number 11, let's say I give you're gonna measure the height of my Gatorade bottle, okay? And you take a ruler and you're gonna measure this. And you write down, Mr. Burkamp, I've measured that, and I think that's 12.65 centimeters. Okay, let's say this is what you tell me that it is. So here's what I'm going to assume when I see your measurement. That you knew for certain the 12 and the 6. So what I'm going to think, here's what I'm going to think. Your measuring device is 12, 13, and I'm drawing this really, really big. Okay? This is how I think your measuring device is marked off. You know that the height of that Gatorade bottle is somewhere, somewhere between 12 and 13. There's no uncertainty in that. You know that it's somewhere between 0.6 and 0.7. You know that. And you estimated the 5. So when you see a measurement, your first values are known. This is the one that you guessed. So there's no uncertainty in this. Your uncertainty is in the last digit. So here's how you can answer it. You can say the last digit is an estimate while the other values are known. You can do something like that. Okay? Angel, are we good? Good. Anything else at all? Yes. Is this going to cause me to have gray hair?
Can you go over 14?
14? Yeah. Okay. So here's the story. You have 4.100 times 10 to the 8th meters per second. And we're going to divide that by 7.50 times 10 to the second seconds. Okay? So let's just look at this. Order of magnitude. Don't worry about anything else. I take 10 to the 8th and I divide that by 10 to the second. So roughly, if I take 10 to the 8th and divide that by 10 to the second, what's my order of magnitude going to be? 10 to the 6th. So I know I'm going to get an answer somewhere around 10 to the 6th. Maybe 10 to the 7th, maybe 10 to the 5th, but it's going to be something around there. Okay? Now, let's look at the units. I got meters per second divided by seconds. So what units am I going to get out of this? Am I going to get meters, or am I going to get meters per second squared?
Meters per second squared.
Yeah, because if I multiply by the reciprocal, here's what I know. My answer is going to be something around 10 to the 6th meters per second squared. Okay? And then it's just a matter of plugging numbers into your calculator. Okay? But now, here's the bigger question. On number 14, how many significant digits should you have in your answer?
3.
3. 3 significant digits, because that's the least number of significant values. Bailey?
Okay, so for like the process that we did for 15, we do the same thing for 16?
Yeah,
Okay,
yeah, because you're adding, so it's all about place value,
okay.
okay? All right, anything else? Going once, going to,
Can we round up,
what do you mean?
like, for decimal places, like, if it's, like, say, 6?
Oh, yeah, you have to.
Okay, just.
Oh, yeah, oh, no, believe me, I have never told you, no, you can't round up. So let's say that you get 12.68, okay? And you want to round that to the nearest tenth, yeah, you're going to call that 12.7. If it was 12.62, then you leave it at 12.6. Oh yeah, you can most definitely round up. Most definitely.
Thank you.
Okay. Anything else? Let's go try sold. Okay. Get that handed in.
We should have to do 10 minutes. Do you want that or?
That, you can just put 0.0. You don't have to, yeah. You can leave it there, it doesn't make any difference.
Okay.
Okay, anybody do any sports, track? Okay, Connor, here's what we're gonna do. You got shoes on? Yeah, you look like you're fit. Okay, you even have a Maze track and field shirt on. Okay, you're gonna be able to run it. So here's what we're gonna do. We're gonna go out into the hallway, little field trip, and we're gonna measure out 10 meters, okay? And we're gonna measure how long it takes Connor to run 10 meters. And we're gonna get an idea of how fast he's gonna run. Can you handle it?
Yeah.
Okay, all right, so let's go. So, bring the camera. So, Kevin. Okay, I need you to start, stop, and if you need to reset it, hit that button. And then, there you go. Okay, so let's go. Can you take that and walk that way? Oh, 7. Okay, lay it down. Okay, Connor. Okay, so you guys are your timing, right? So I'm gonna have Connor back here. Now, I want you moving at full speed when you hit this point. Okay? So go however far back you need to go.
Yeah.
Oh yeah, okay, you want to lose speed, okay? So that you're already at full speed. Now, the reason that I want him at full speed is because we're going to take the distance that he's going to travel and we're going to divide that by time, okay? And it's a great equation, but you can only use that if you have non-accelerated motion, okay? Otherwise known as constant velocity. So that's why I don't want him starting from rest and moving the 10 meters, because that means he would be speeding up during his time movement. I want him moving at a constant speed over this time. Okay? So, are you guys ready to do the timer?
You time it.
You time it from where he crosses that point to the point that he gets to there.
Okay.
Okay? Got it? You can handle it. I got faith in you. Okay. You need to stretch? I don't want you to pull my hands or anything.
Good.
Okay? You ready?
Yeah.
Okay, let's go. We'll look at that form. Okay, what'd you get? 0.01?
4-1. Is that 1 second? 1
Yeah, 1.41, 1.32. Okay, because I thought you were saying like 0.01 seconds. I'm like, wow, that's fast. Holy cow, that's like speed of light fast. Okay. Okay. Now, so you got 1 point, and you got. Okay. Oh, yeah, that's comforting. Great. That's our alarm system. Just fell out. Okay, whoa, yeah. Connor, yes, a great example. Okay, so we got 1.31 and 1.41. Okay, roughly. So do you think this is how we do timing events at Olympics? Where you have one person kind of going boom, boom. No. Okay? So this is the classic example of we're going to kind of have some sketchy data. Okay? It's like not a fault of yours, but you guys are trying to guess when he started there, and you're trying to guess when he ended up there. So when we take that distance and divide it by the time, I can't say, oh, Connor's velocity is 8.312464, but whatever my calculator said. So when I calculate this velocity, I have to keep in mind that I kind of had some sketchy data collection, okay? And it's about 10 meters. Like, we stretched out the tape, we had it down there, boom, here we go. Now, in the Olympics, they have lasers on each end. You know, he would break the beam on one end, he would break the beam on the other. So they would know exactly that amount of time, okay? So this is, it's kind of a ballpark. We got some sketchy data. Got the idea. Ready? Go. Back we go. So what were the two times that you guys got? 1.32 and 1.41. Okay? So we have about a 1/10 of a second difference between the two, which isn't bad. Okay? So I've got the two times, so what can I do with my two times? Average. Okay? So if I average these two times, I'm probably going to get, so I'm going to take 1.32 or 1.41. And then divide that by 2. 1.3 something. 1.365. So let's call it 1.37. Okay? Now, even on the average, because your calculator is going to tell you the average is 1.365 seconds. That's what your calculator is going to give you. Okay? But here's the deal. And this is the whole process. If you use 1.365 seconds, I'm going to think your timing devices went to the tenths, the hundredths, and the thousandths place. Okay? It didn't. Our timing devices only went out to the hundredths of a second. So when I calculate this average, I can't make my average look more precise than the times that I used to collect that data. Okay, so this is why I've got to call this 1.37 seconds. So what we're going to use is we're going to take velocity, and we're going to take distance and divide it by time. And we're going to use this a lot, okay? But I'm just going to begin to plant this seed. This is a great equation, and it works beautifully. We're going to use it. But listen to me. You can only use this if the object is moving at a constant velocity. If you're speeding up, slowing down, I can't use it. So this is why I had to have Connor running at full speed when he did this. I didn't want him starting from rest and then speeding up and then going. This is why I wanted to make sure he was at full speed when he crossed that point. Okay, so I got 10.0 meters, okay? 10.0 meters, how many significant digits? 3. 3, right? There's a decimal place. Decimal place you count right. So there's a decimal place, this has 1, 2, 3, 3 significant digits. So in other words, well, and that was probably realistically, I'm not gonna say Connor ran 10.000 meters, okay? I didn't set this up with the transit and lasers. I laid out a tape measure. How far did he run? 10 meters, okay? We're probably solid estimating the 1/10 of a meter. Okay, that's cool, right? Then we've got a time of 1.37 seconds. So everything has 3 significant digits, right? So somebody take 10 and divide that by 1.37 and let me know what the oracle says the answer is. Jaden, what do you get when you take 10 and divide it by 1.37?
7.29927007.
La la la. Okay? Now, this is the oracle says here is his velocity, right? 7.299, whatever that is. So here's the deal. If this is what you write down as his velocity, I'm going to think you had phenomenal data. You had laser beams on each side. You laid it out. You knew exactly 10 meters. You had phenomenal data. If this is what you write down as his velocity. Okay, this is where the door has to swing both ways. But you look at this and go, not really. It's like we had 2 people kind of guessing when you started and when you stopped. Then we took the average of those 2 times. That's about 1.37, okay? We kind of guessed the 10 meters, right? So this is why I can't write that down, because I don't have that good of data. So what I could write, it was 7.299, okay? So what if I just write 7.3? Is that okay? Bad. Connor, why?
It's not precise enough.
Yeah, it's not precise enough, okay? Since it worked out to be 7.299, how am I going to write, how can I round that and still show 3 significant digits?
7.30.
7.30 meters per second, okay? Now, to give you some perspective, world-class, absolute world-class top-end sprinters will run the 100-meter dash in about 10 seconds, okay? So if you do the math, and that's starting from rest, okay? So world-class sprinters will run a 100-meter dash in about 10 seconds, which means they're running at about 10 meters per second. So if you want to be a world-class sprinter, Connor, you need to get this up to about 10 meters per second. So in other words, you need to run that distance in about 1 second and not 1.37 seconds. Okay?
Correct. I do the hurdles, so
Oh, there you go. Okay. Oh, you're a hurdler.
yeah, it's special.
Oh.
Sprinters.
Yeah, okay. But okay, so if you want to change races, okay, that's what you're gonna have to do. There's your goal, right? Okay? So I do this, the reason we do this is that so you have an idea of some different velocities. So if you're running, okay, and that was full speed run, okay? That wasn't just a jog. That was a full speed run, 7.3 meters per second. So if you're dealing with a human walking, running, something like that, that's kind of your top end. For example, let's say you talk about the velocity of a dog. Do you think dogs run faster or slower than humans at a full speed?
Faster.
Faster, okay? Typical dogs run faster. So dogs might run around 10 meters per second, let's say. If you're going 70 miles per hour out on the highway, that's about, I can never remember that number, that's about 30 meters per second, okay? So 70 miles per hour is about 30 meters per second, okay? So I do this because you all aren't used to thinking of velocities in terms of meters per second. You're used to thinking of velocities in miles per hour, okay? So here's another application you can have of this. Let's say that I'm going to take this rubber stopper and I want to swing this thing around over my head like this, okay? I want to determine how fast that rubber stopper is moving, okay? So this is going around. I want to try and get an idea of how fast that rubber stopper is moving. So what are some things that I can measure? Derek, what's something that I can measure?
Like the length of the, like, road that you're wanting, so you can find the radius.
Oh, I can measure the radius. Oh, that's a cool idea. So I've got this thing going around, and I can measure the radius, let's say that's 0.80 meters. So if I know the radius, it's about 0.80 meters, what could I find knowing the radius? Huh?
Circumference.
Circumference. How do you calculate the circumference of a circle? Knowing the radius. No, that's area.
It's,
Somebody said, Jaden, what did you say?
pi times diameter.
Yeah, pi times diameter or 2 pi r.
Yeah.
Okay? So if I find the circumference of this, that's going to be 2 pi r. Okay, so I have enough information I can calculate the circumference. So I know the radius, so I can figure out how far the rubber stopper travels. Okay, so now I have the distance. What else could I measure?
Could you like stop and then like the time it takes to get around once?
Yeah, I could take a stopwatch and I could sit there and go, okay, start it, stop it. Okay, just like we did with Connor when he was running. Okay, I could pick a point and I could go boom, stop. Okay, when he gets back to that point. So I could measure how much time it takes. Now, when you talk about time for something that's traveling in a circle, and we're going to use this with planets, we're going to use it as a planet as it spins on its axis. Anything that returns back to the same point, we're going to refer to that as the period of one revolution. So here's the difference. So I could measure that, let's say, I don't know, I'm going to have that as 1.20 seconds. I timed it, took about 1.20 seconds to go around. So here's the difference. When Connor was running, he was just going a set distance. He was just going in a line. We use lowercase t because that's just time. When you have something that is repeating, then we're going to use uppercase T because uppercase T is going to stand for period. Okay? So when you see uppercase T, that's period. And you can do the same thing and you use that even with like when you have a spring, okay, that's oscillating like this. So that spring, that mass is going back and forth like this. So we could measure how long it takes to go from here and then come back to that point. Okay? So that's something that we could do. If you talk about going around in a circle, if I turned this into a pendulum, okay, and made it oscillate back and forth, I could talk about how long it takes for that thing to oscillate as it goes back and forth. So anything, whether it's a planet, an oscillating mass, a pendulum, if we took Connor out to the track and we made him run around the track, okay, then we could talk about periods. Like, oh, how long does it take Connor to run around the track? Okay, so lowercase t is just a one-time thing. Uppercase T is going to be something that's going to return to that same point in space. So if I wanted to calculate the velocity of that rubber stopper, what I'm going to do is I'm going to do a very fancy version of what we just did with Connor. We're going to take distance and we're going to divide it by time. But I'm going to write that as 2 pi r over t. Okay? But don't flip out and go, oh, look, that looks so complicated. Oh, all it is distance divided by time. Okay? That's all it is. We're going to figure out how far this thing is going to go and how long it takes. Okay, that's it. It's just distance divided by time. It looks fancy. It's not. It's distance divided by time. So in this situation, I'm going to take 2 pi times 0.8 meters and then divide that by 1.20 seconds. The top number gives me how far the rubber stopper is going to go. The bottom number tells me how long it's going to take. Okay? It's just distance divided by time. Okay? It's nothing new. It's distance divided by time. Okay. Now, let's apply this to a little bit bigger situation. So here's our star, which we've called our sun. And here's the planet Jupiter. And Jupiter has an orbital radius of 7.781 times 10 to the 8th kilometers, and an orbital period of 12 years. Okay? So it takes the Earth 1 year to go around our star. It takes Jupiter 12 years to go around our star. So if you like birthdays, don't go to Jupiter, okay? Because you're only going to have a birthday like every 12 years if you consider a year being like, one lap around the sun, okay? So if you like Jupiter, or excuse me, if you like birthdays, Jupiter is not your thing, okay? Now the cool thing is on Jupiter, if you go around twice, that's like, 24 years. It's like, what's the drinking age on Jupiter? 2. Well, that's cool, right? It was actually 24 years on Earth. So I want to figure out how fast Jupiter is going to be moving around the sun. So all we're going to do is we're going to take that same idea as we did with the rubber stopper, and we're going to apply it to Jupiter. Okay, literally, it's all we're going to do. We're going to go, velocity is going to be 2 pi r divided by t. I promise you, on the assignment for tomorrow, you're going to have a problem like this. On the test on Tuesday, you're going to have a problem involving this. And I will give you the equation on the test. It's going to be on the second page. It's going to be on the back side. I'm going to give you this. You don't have to memorize it. You just have to know how to use it. Okay? So I promise you, if you hand in the test on Tuesday and you go, I haven't used 2 pi r over t, you have done something wrong. Okay? But I'm going to give you the equation, so don't flip out. So in this situation, I'm going to take 2 pi times my radius of 7.781 times 10 to the 8th kilometers. Now, I want to figure out how fast Jupiter is going. The first thing I want to do is figure that value in kilometers per hour. Okay? So I want this in kilometers per hour. So I got 2 pi times r. That number alone gets me the distance that Jupiter is going to travel as it goes around in this orbit. Okay, that's the first thing it's going to get. Period is going to be 12 years. So, what am I going to have to do with the years? Tyler, I want kilometers per hour. I got kilometers per year. So what am I going to do?
Hours per year, find the conversion.
Yes, I got to get years into hours.
Hours.
So 1 year, let's start with this. 1 year is how many days?
365.
365 days. So if I stop right now, what units would I have? If I don't do anything else, I would have units of kilometers per day, right? If I don't do anything else, I would have kilometers per day. It's not what I want. What do I want? Kilometers per hour. So now I need to go 1 day is how many hours?
24.
24. Okay? 24.0. So now, if what I'm going to have is up top, I'm going to have units of kilometers. Then I'm going to have hours down here. I'm going to have kilometers per hour. Now, at this point with your calculators, and you all have very, very good calculators, okay? There's a couple ways you can do this problem. One option is that you go through and you find the distance, okay? You take 2 times pi times 7.781 times 10 to the 8th, and you get an answer. And then you take 12 times 365 times 24, and you get an answer down below, okay? And that's cool. If you like to do that, that's fine. But if you're going to do that, don't round your answers until you get to the final step. So in other words, don't round those kilometers, don't round the number of days or hours. Keep them all together, okay? That's an option. Okay, if you like to divide and conquer and do those numbers separately, that's cool. The other option that you can do is do it all at once. You would take 2 times pi times that distance. and then you would divide it by, now here's what you have to be careful of. If you're gonna do this all in one step, you need to put this whole thing 12 times 365 times 24 in brackets. Okay, because if you don't put that in brackets, and if you just put divide by 12 times 365 times 24, what's gonna happen is that your calculator will follow the rules of algebra, and it will divide by 12, then it will multiply by 365, and then it will multiply by 24, and you're getting an answer that makes no sense at all. Okay, it will make no sense at all. So, I don't care how you do this, that's what you got. So you can either divide and conquer or do it all at once. It's however you feel comfortable using your calculator. Now, 12.0, how many significant digits are in that? Jaden, how many significant digits? 12.0.
3.
3 significant digits. Bailey, 7.781 times 10 to the 8th kilometers. How many significant digits are there? 4. So I have 3 significant digits and I have 4 significant digits, and I'm dividing. So how many significant digits can my answer have? 3. So somebody do the math and let me know what you get. Give me that answer in scientific notation with 3 significant digits. Peyton, what'd you get?
4.65 times 10 to the 5th.
Times 10 to the 5th? Anybody else get that? Derek, what'd you get?
I got 10 to the 4th.
Yeah, that's what I
I
got.
got 10 to the 4th.
You got 4.65 times 10 to the 4th?
Yeah.
Okay. There's a slight discrepancy there, kind of an order of magnitude.
It's 4.
It is to the 4th? Okay. 10 to the 4th, okay? So that's how fast Jupiter is moving in kilometers per hour. Now, the next thing I want to do is I want to convert that into meters per second. And I promise you, this is what you got to be able to do on the homework. This is what you got to be able to do on the test. If you hand in your test on Tuesday and you haven't done this, something's wrong, okay? So, here's what you need. Take that 4.65 times 10 to the 4th kilometers and put that over 1 hour. All of these problems work the exact same way. And if you get in that habit that it eliminates, oh, how do I do this? What's my guesswork? Just do them all the same way. So down here I'm going to put 1 kilometer. Up here I'm going to put 1,000 meters. Up here I'm going to put 1 hour. Down here I'm going to put 3,600 seconds. So my hours cancel out. My kilometers cancel out. I get meters per second. So the short version is I'm going to multiply, if you don't like zeros, I'm going to multiply by 10, and then I'm going to divide by 36. So somebody take that answer, multiply it by 10, and then divide by 36. What do you get? Jaden, what'd you get? In scientific notation, 3 significant digits.
1.29 10 to the 4th power.
To the 4th meters per second. Okay? Now, that's actually faster than the speed of sound. Okay? Which is, it's okay. Space is a vacuum, so you don't have to worry about traveling faster than the speed of sound. That's okay. You can do that in space because there is no atmosphere to move through. Okay? So, there you go. This is something that you have to be able to do, I promise you. Okay? It's going to be on your assignment today, and it's going to be on the test. You're going to have a problem just like this. The only thing I'm going to do is I'm going to choose a different one. I might choose Mars. I might choose, Neptune, but it's the exact same thing. And I'm gonna give you that equation, you just have to know how to use it. Okay, so. Okay, let me get you started on this assignment. So this is kind of summary of everything that we have done. So you all have the skills now to do physics. You know how to do dimensional analysis, you know how to write your answers, you know how to measure things, you know how to do experiments. So this is just a summary of all that. So when you get to question number 4, okay? You're going to look at a relationship between how fast the car is going and how far it takes to stop. Okay, so those are going to be your two variables, velocity and stopping distance. Which one are you going to control? How fast you're going or the stopping distance?
How fast you're going.
Yeah, you're going to control how fast you're going. So is your velocity your independent variable or your dependent variable?
Independent.
Velocity is your independent variable. Beautiful. Now, when you get to this question, I'm going to tell you that that relationship is expressed as d equals kv squared. So what you want to do, and I've given you this space here, you're going to try and figure out, using the process of dimensional analysis, it is a process, you're going to try and figure out the units of k. Right? That's what you're going to try and do. So you're going to go, oh, velocity, meters per second, distances in meters. Put in the units, just like you all did on the assignment on dimensional analysis. You all have that assignment back. You're going to find the units of k, and then I'm going to ask you, what do the units of k represent? So if you do this right, when you get the units of k, it is going to be the inverse of a known quantity. Like it's going to be the inverse of time, or the inverse of mass, or the inverse of velocity, something like that. So when I ask you, okay, what physical quantity does this represent? You're going to show me k has units of, boom, whatever. Then you're going to tell me what that represents. Now here's how you can check that you got k right. If you want to make sure these units are right, substitute them in for k, multiply that by v squared, see if you get units of meters. Okay, that's how you can check that you got it right. If you don't get the units of k multiplied by v squared, if you don't get meters, you've done something wrong. Okay? When you get to questions 5, 6, and 7, these are just algebra problems. Do not do dimensional analysis on 5, 6, and 7. All I want you to do is solve for a particular variable. So like on number 5, you have a equals v squared over 2d. All I want you to do is get v by itself. It's an algebra problem, okay? Multiply by 2d, take the square root of it, okay? That's all you have to do. So when on these blank spaces over here, when I give you an assignment like this, and I give you spaces, this is where I want you to write your answers. Okay, so anytime, that's the magic code. When I give you an assignment, I don't like answers randomly written down all over, because then I have to search for them. This is why I gave you spaces. That's where you're going to put this. Now, when you get to number 8, I've given you this equation. Period equals 2 pi times the square root of L over G. So what this represents is the period of a pendulum. So notice here I'm using uppercase T, just like I did when I talked about Jupiter. I'm using uppercase T because of the fact that I'm using that as the period of a pendulum. How long does it take to go from here and come back to that point? So this is what that equation is giving you. So L is the length of the pendulum, G is your gravitational acceleration. Okay, like on Earth, it's 9.8 meters per second squared. If you're on the moon, it's 1.63. Okay, so G is just your little g is your gravitational acceleration. It's a very specific acceleration depending upon where you are in the universe. So the first thing I want you to do is to get L by itself. Okay, so at some point you have to undo that radical. So how are you going to undo that radical? Izzy, what are you going to do?
Square it.
Yeah, at some point I got to square this thing. Okay, so what I would recommend, I would divide by 2 pi, and then that's the square root of L over G. And then I would square both sides. And then I'd get t squared over 4 pi squared equals L over G. Now, there's 3 things that I dislike: frizzies, fractions, and freshmen. Okay? So what I would recommend at this point, I know you all have done this, I would cross multiply. I would take gt squared equals 4 pi squared L. Once you get it as like a linear type thing without those fractions, then it becomes very easy to solve. Then you can solve for L, you can solve for little g, you can solve for t. So what I would do, once I got here, I'd cross multiply and go gt squared equals 4 pi squared L. Now, if you want to get fancy, if you want to check your game in terms of your skill level, when you get this thing solved, you're going to have L is going to equal something. Okay? L is a length. If you want to check your dimensional analysis skill level, when you get this equation, do dimensional analysis and see if you get units of meters. Okay? If you do, you did it right. If you do dimensional analysis on what you have and you don't get units of meters, I promise you it's wrong. Okay? So on B, on the back side, you're going to take that equation that you just used, and you're going to figure out the length of the pendulum it takes for me to have a period of 1.5 seconds. So in other words, how long do I need to build that pendulum so that when I let go of it, it takes 1.5 seconds to go from here back to that point. Okay? That's what you're trying to do. Now, when you get to C, you want to go back and solve that equation for little g. Okay? So when your answer for C, what I would recommend is that you go back to this, cross multiply again, solve for little g. And again, if you want to check that your answer for C is right, see if you get units of meters per second squared. If you do, you probably did it right. If you don't get meters per second squared, I promise you it's a train wreck. When you get to number 9, okay, we're going to talk about the Earth, okay? So on number 9, again, I've given you that equation. V equals 2 pi r over t. This is how it's going to play out on the test. I'm going to give you that equation. You just have to know how to use it. So what you're trying to figure out is that we're going to talk about the Earth. So here's the sun. Here's the Earth, obviously not to scale. And we're going to try and figure out how fast the Earth is moving as it goes around the sun. So it's just like on a big idea is this same idea. If I want to calculate how fast that rubber stopper is going around, I figure out how far it goes, I find the circumference, and then I divide it by how long it takes to go around. Now, how long, on number 9, how long does it take for our rock to go around our star? What'd you say?
Okay.
No, that's how long it takes to spin on its axis.
365 days.
10 to the 8.
No, that's the radius. How long does it take for
1
the
year.
Earth to go from here all the way back to that one point?
1 year.
1 year,
365.
365 days. So on number 9, on that period, you're going to use 365. Now, if you want to get fancy, if you really want to get fancy, technically it's 365.25 years. But you can just use 365 if you want to. it's technically 365.25, which is why we have to have a leap year every 4 years, because technically takes us, that's days, not years. That's a big difference, okay? Technically, it takes us 365.25 days, which is why we have a leap year every 4 years. Okay, so that's gonna be T. I've given you the radius. You're gonna have two answers. One in kilometers per hour, one in meters per second. Now, when you get to number 10, on number 10, we're gonna talk about the Earth as it spins on its axis, like this, okay? So imagine that, here's Albert Einstein, we'll use Big Al, and here he is in the equator, and he's here, and the Al is gonna spin around like this. I wanna know how fast Al is going as he's riding our spinning rock as we spin around on our axis. So, on number 10, you're still going to use that same idea, V equals 2 pi r over t. I've given you the radius of the Earth, 6.37 times 10 to the third kilometers. So there's your radius. Now, Angel, now how long does it take for our rock to spin one time on its axis?
On its axis, a day.
1 day. So on number 10, you're going to use a period of 24 hours. So on number 10, T is going to equal 24 hours. On 9, T is going to equal 365 days. Okay? When you get to number 11, and I'm going to give you just a half sheet of graph paper. On number 11 is the only one that you have to graph. Okay? You're going to have force and you're going to have acceleration. If you're not sure how to graph that, go back and look at that graphing assignment that I just gave back to you today, okay? So if you don't know, if you don't remember how to graph that and what the slope represents, go back and look at the assignment that I just gave back to you today. It's the exact same thing. Then you're going to have a bunch of questions to answer on that. You're going to have to find the slope, make sure that you put the units on the slope. When you get to number 12, okay? When you get to number 12, what we're talking about in number 12 is that here's the Earth, and we're going to shine a beam of light around the Earth. So in number 12, you're going to still talk about 2 pi r over t. So in number 12, I've given you the velocity, I've given you the speed of light. You're going to know that number. You're going to know the radius of the Earth, okay? What you're trying to figure out is period. How long does it take for that beam of light to go around? Don't worry about answering 12b. I'll get to 12b tomorrow, okay? And then you have number 13. That's just, hey, is it going to double? Is it going to triple? Is it going to be half? That type of thing. So let me give you all a half sheet of graph paper. You're on your own. Stop yonder camera, please.